Thank you. Good afternoon. My name's Rishiyur Nikhil. Just call me Nikhil if you want to use one name. I write it backwards in my part of the world where I come from. I'm spent about 7, 8 years, 9 years as faculty member here at MIT. Then I worked at Digital Compact Research Labs for another 10 years or so. And I've been working with various small companies, but generally around this topic of Bluespec for about 20 years now. So I'm going to, probably everybody might have heard about Bluespec, probably not too many people know much about what it is. So I'm going to say a little bit about that. And then I've also developed a new textbook and some teaching materials on that, so I'm going to talk about that as well. Okay. So the key points summarized on this slide, and then I'll elaborate for the rest of the talk. One is that Bluespec is actually two syntaxes for one language. It started out with a very Haskell-like syntax. In fact, you'll see in a moment, it borrows lots of ideas from Haskell. And when we took it out as a commercial product, that didn't fly at all in industry. So we developed a new front end with a more system Verilog-like syntax. That's called BSV. So BSV and BH are really two languages, just two different parsers in front. Everything else is exactly the same, and they can interoperate. In other words, you can write modules in BSV and modules in BH and interoperate, et cetera. It's definitely industrial strength. It's been now it's coming on 24 years out there since the very first lines of the compiler were written. There's been many ASIC and FPGA products out in industry using Bluespec. And it's very stable. So it's not a moving target. It's not a research language. We're not continuously changing it or anything like that. And it's been open source now for about 4 years. January 2020 is when we open sourced it completely. So it's all on GitHub, by which I mean the source code for the compiler, libraries, everything is, and documentation is up all there. And there's also some discussion groups open online. There's a new textbook. I'm going to talk about that, which tries to teach these two topics of learning a hardware design language, in this case BSV, on the one hand, and learning how to define a pipeline RISC-V CPU. And these two things mesh well because the RISC-V CPU provides good examples for teaching BSV. And as part of that, there are two CPUs that are provided with it, called Drum and Fife, respectively, and they both are FPGA runnable out of the box. Okay, and there are more resources, but I'm not going to spend time today talking about it. There are more RISC-V CPUs. Piccolo, Flute, Tuba are 3 different CPUs that Bluespec ourselves have been involved in. Tuba actually started out at MIT, and then there were additions at Bluespec, and then University of Cambridge has done more work on it. The Cherry RISC-V work that is done at University of Cambridge is all written in Bluespec, and those are also available open source. And then there's other little IP pieces like the interrupt controllers and timers and debug modules and things like that are available also on the web. Okay, so in fact, that's the takeaway for the whole talk. Now I'm going to delve into a little more detail in the first 2 points, namely the languages and the textbook. So let me talk a little bit about the languages. So we are very much inspired by ideas from modern programming languages. And the things on the right you can see are, in fact, the inspirations for Bluespec. So whenever you're designing a circuit, you can think of it as you're doing 2 different activities, 2 related activities. One is you're describing the structure of the circuit. What are the pieces? How do they connect together? What kinds of hierarchies do they form? That kind of thing, which is, you can think of that as a structural description of what you're building. And then once you have described the circuit, then the question is, over time, how does it evolve? What is its behavior? So for the first part, which is circuit description, most of our inspiration comes from Haskell. So we take essentially Haskell, lock, stock, and barrel, syntax for the BH version of the language, the full functional programming capabilities that you have in Haskell, its full type system, including algebraic types, polymorphic types, type classes, all the stuff that you see there, is all those ideas taken fully from Haskell. From system Verilog, for the BSV language, we take the syntax, so types, modules, things like that are all described using system Verilog idioms. And then the programming in the large, that is when you do multiple files, packages, imports, exports of names, all of that is taken straight from system Verilog. And to those, we add some of our own things. One is that to the Haskell type system, we add a certain kind of second order types that involves numbers and strict static type checking of numeric constraints so that you can get exact bit width descriptions, exact bit width matches, and you can do this polymorphically also. So you can talk about a function that takes an n-bit vector and an m-bit vector and produces a concatenation with an n plus m-bit vector, for example, and leave those as parameters, but still have it completely statically checked, so you don't accidentally drop or add bits here or there. So that's the type part of it. And then we've also added the capability of doing multiple clock domains. So you can build circuits that have multiple clocks. And we do strict static checking of clock domain discipline, namely that signals don't cross domain boundaries except through synchronizers. So that's all about circuit description. For circuit behavior, we are inspired particularly by a class of languages called term rewriting systems. And examples in the software specification space you might have heard of are TLA+, Unity, EventB, and so on. All of these are talking about concurrent state transition systems, which is exactly what hardware is. It's a concurrent state transition system. The key thing in term rewriting systems is the property of atomicity of state transitions. So you can talk about big state transitions as an atomic transaction, and this allows the concurrent activities that are going on to interact meaningfully. That is, that they're not seeing inconsistent views of state in what they read and what they write. And that's basically what comes into BSV. So we've added that, and what we've added on top of that is a way to build these atomic transactions incrementally and modularly, so that an atomic transaction can involve a rule that's in one module that may involve a method that's in another module, which may in turn call a method in another module, and yet they are globally guaranteed to be atomic. And what that allows you to do is to reason about correctness with a very much more powerful reasoning mechanism than if you were just working with clocks. We also have capabilities to directly import Verilog, to import C, etc., so you can mix and match with existing IP with C models and things like that. So those are the things that come into Bluespec. Despite taking ideas from this, we're not embedding ourselves inside a Haskell compiler or something else. It's a standalone, purpose-built compiler for the BSV and BH languages. And that's, like I said, 20 years in the making, more than 20 years in the making. The original ideas for the behavior part, in fact, that was the key kernel of where we started the Bluespec work with. That came from James Hohen-Arvind here at MIT back in 1999. And Leonard Augustin, who's a well-known name in the Haskell community, was actually the first implementer of our compiler way back in 2000. Okay, the second topic I want to talk about is the book. This is a book that I have just recently been writing. And I know it's old-fashioned to look at printed paper, but there is a draft here, which is about 300 pages. And I have 2 copies here. I'll leave it here if you want to peruse it. And if you'd like to have a copy, feel free to take one with you. So I'll just leave that over here. And it's on GitHub. The link is shown over there. And what the GitHub thing has is it has the full PDF of the textbook. So you can just peruse the PDF if you like. There's some full source code. I'll explain what those source codes are in a second. And I'm in the process of developing lecture slides and exercises, which will happen over the next 6 weeks or so, because I'm actually teaching this course starting on Monday with this. So the approach is, first of all, to do these things in an interleave manner. That is, we're trying to learn the language, and we're trying to learn pipeline CPU design. And so the whole thing has been structured in a way by which, like a gradual learning curve, you can incrementally learn more and more about BSV and keep applying what you've learned to actual examples from the CPUs that we're going to end up with, right? And even there's a learning curve gradation in the sense that first we do the CPU that is called drum, which is just an FSM sequenced CPU. In other words, it literally reads like a simulator you might write in any language, where you do a fetch function call and a decode function call, a register read function call, and so on and so forth. But it's all synthesizable. You can actually run it on an FPGA. But it's very easy to follow what is going on, and it's the first canvas on which you kind of resolve any questions you have about what is RISC-V, what does this RISC-V instruction do, and so on and so forth. And you can resolve all of that without thinking about having to worry about pipelining and so on. Having done that, we move on to Fife, which is in fact a pipelined CPU, and it brings in all these kinds of issues which are unique to the fact that you have a pipeline CPU. But now we can focus on these issues without having to go back to ask questions about RISC-V and what is RISC-V about, and so on. So it separates the issues of what is RISC-V from how to deal with pipelining itself. So that is the approach taken in the book. So incremental, both in BSV and in how you learn RISC-V. Okay, so let me see, what else do I want to say out here? Yes, the right-hand side of the slide is just saying, of course, the book and the examples are all RISC-V CPU-based, but the language is not specifically about CPUs. It's like Verilog or System Verilog. It's a general-purpose digital design language. So once you've picked up what you've picked up so far, you'll be good to also tackle other kinds of IPs like the ones shown on the right. Okay. So there's a lot of topics we cover in the textbook. This is sort of, we don't do too much on the left, although we do need the following, which is in order to run something on your RISC-V program, you need to know how to compile it and build ELF files and memory hexes and so on, things like that. But the focus is here on the right side. We go from the CPU, and we go through the path on the right, which is it's coded in BSV, run through the BSC compiler. That produces Verilog RTL. We show that in Verilog simulation, basically using Verilator as our simulation tool. And we also show it in FPGA synthesis using the Amazon AWS F1 instances. But in principle, you could run that Verilog through whatever flow you like. Okay. So it comes with a test bench, which basically assumes separate IMEM and DMEM channels and split phase memory requests and pipelines, so that you can simultaneously do instruction fetch and DMEM, and also within each of those you can simultaneously pump in requests as you're pumping out responses from memory. And as you run these simulations, you get a full stage by stage trace output. We have make files to do all the builds on the GitHub site, and we have instructions on how to do it on AWS. In the course, when I'm teaching it live, we actually show people how to do it, but we'll have a document on the website on how to do that if you want to do it yourself. So there's also chapters on debugging, verification, optimization, and so on. So the idea is in all of these cases to first present the simplest way of explaining these things. And then in a subsequent chapter say, okay, now take a look at this, and here's the problem in terms of performance. But here you might lose a cycle here, you might lose a cycle there, et cetera, and here's how you can fix it. There's also a very little bit of a pipeline visualization tool, by which I mean you want to see with instructions going down the x-axis, the y-axis, and time going across there. So for every instruction, you can see here it's in the fetch stage, here it's a decode stage, here it's in the register read stage, and you can see pipeline bubbles and things like that. That's actually done with the same trace tool. We just post-process the trace to produce a CSV file, and you can load it into any spreadsheet and then use the spreadsheet grid as your pipeline visualizer, Excel or OpenOffice or anything you like. Okay, so I think that's actually all I had to say. This slide just repeats my key points. So the languages are very stable, they exist there, so I encourage you to look at it if you're interested. And we have forums where people discuss about the language, questions, etc. In terms of educational materials, there's a fair amount of other training material, but it's kind of all over the map. In some sense, this book is the first sort of comprehensive, let's go right from start to beginning, assuming you know nothing before this about digital hardware design and assuming nothing, you know nothing before this about RISC-V pipeline design. So it has very minimal assumptions at the start. It takes you all the way through, and it comes with the complete source codes, etc. So I'll stop there, leave this slide up for links if you want to take it down or take a picture now, but also the slides will be up on the Latch-Up website, so you can certainly take it later. They're all hyperlinked, so you can actually click on them and go to the appropriate places out there. Questions?
So thank you. Do we have any questions from the audience? Over there.
Thanks for the talk. Just kind of a general question. If I already use, Verilog, I do some Amaranth. That's where I focus a lot of my dev on this front is in Python. So if I was going to say, okay, I'm curious, what's the major selling point? Why would I invest into learning either BSV or BH?
Okay, so I think the point would be a similar point that anybody using a high-level language would use, right? Why use a high-level language instead of some other language, right? Then we might get into arguments and debates on, is it high-level? What is high-level about it? So I think both in, for example, in Bluespec and in Chisel, we're essentially using languages like Scala and Haskell as the level at which we do our conversation, right? And neither Verilog, even system Verilog, even though that has enhanced some of those things, does not reach to the same level. So in terms of high-level programming. The second thing I should say, which is a unique selling point for Bluespec per se, is the thing I said about atomic transactions, right? So, which is that we're dealing with extremely parallel concurrent systems when we're dealing with hardware, right? And that's hard, whether it's in software or in hardware. And one of the reasons it's hard is because of consistent view of state. You have different concurrent processes that are running, that are examining state, that are updating state, etc. In software, it's been a long accepted thing that atomic transactions is what saves you, right? You see it in database systems, you see it in operating systems, you see it in parallel software, concurrent software. You don't yet see that concept in any other language, and we're trying to bring that into the hardware view of the world, etc. And I'll give you a very small example. Suppose I ask you to design a up-down counter with a clear, where I can say increment by n, decrement by n. These are two possible transactions you can have with it, or clear it back to 0. All right? Well, all kinds of ordering questions come up, right? Which is, suppose I try to increment and decrement on the same count. What happens? Suppose I try to increment and clear on the same cycle. What happens, right? So it's a question you have to think about whether you're doing schematics or Verilog or system Verilog or Bluespec or Chisel, right? But what Bluespec is giving you a vocabulary to talk about ordering. So you can specify in Bluespec these things at a high level. Oh, when I do increment and decrement at the same clock, I want it as if the increment happened first and then the decrement happened. So for example, particularly if it's a saturating counter, increment before decrement is different from decrement before increment. And if I do a clear, do I clear it and then I increment it so I see the final value after the increment, or do I increment it and then clear it so I see 0 at the end? So those kinds of ordering questions, and this thing scales. You see it all over the point, right? So if you're doing a highly pipeline processor, right, you have a reorder buffer, for example, right? There are 3 different things at the fetch unit, at the retire unit, something else, that are all trying to change multiple things in that reorder buffer, right? So by being able to express it in terms of atomic transactions, you're saying these things at a very high level, exactly what you want to be atomic, and you're letting the control logic that has to exist anyway. Even if you were doing it in Verilog, you have to build that control logic, and here that control logic is being produced for you by the compiler. So that's it's very hard to convey the value of that in a 2-minute spiel, but that's basically it.
Does the book cover formal verification?
No, we don't cover formal verification. This is meant to be a very introductory book for people.
But the language.
But the language is built. In fact, it comes from all the languages that I mentioned that were the inspirations on ternary writing systems, Unity, TLA+, and Event B. They are all languages for formal verification. So we're taking those ideas directly into this. And there are people who have been doing work on formal verification with this, but the book that I just showed you does not actually, it mentions a little bit of it, it discusses a little bit of it, but doesn't go into that.
Okay, thanks a lot.
Yeah.
Nikhil, you mentioned in your talk that the book presents first the single cycle CPU and then the 5-cycle CPU, and that they are, as far as the RISC-V aspects of them, the same, and the difference is the pipelining components. I think the repository structure that you have a separate repository for each core. What am I going to see if I look at those repositories in terms of the shape?
No, this book has a single repository that has all the codes in it. They're just two different. So in the directory, you'll see a source common directory, which is all the common RISC-V stuff. You'll see a source drum, which is just the FSM sequenced version of the thing. You'll see a source 5, which is just the pipelined, the top level pipeline versus the top level FSM sequence. And then there's a source common, which is the outer level test bench and the memory system and the UART and those kinds of things, which are shared by all of them. So it's just the CPU, just that layer of the CPU, which is FSM sequence versus pipeline, are in two separate directories, and they're completely interchangeable, and they're exactly the same, because they share all the RISC-V stuff, they execute exactly the same ELF files and so on.
Okay.
Yes.
Do the same resources exist for BH? It sounds like you write a lot of documents for BH.
So let me repeat the question. He asked if the same resources are available for BH, and BH being the Haskell syntax front-end version of it. And at the moment, no. But that's something I've been thinking about hard, which is to essentially make a version of this book with BH instead. I've used my document preparation thing with a view to being able to substitute in the Haskell version of the thing. That hasn't been done yet, but that's a good point. We have a very schizophrenic clientele for Bluespec. There are people who love the Haskell syntax and can't stand the system Verilog syntax, and vice versa, right? But they're all friends. Our primary audience has been the people who use the system Verilog syntax. So a lot of our training material is all BSV based, but we're gradually ramping up the BH side of it to appeal more to the Haskell side of things too.
So we are a little bit behind schedule, so I will cut questions here, but you can ask Nikhil after the talk, I guess. So thank you again.
Thank you.